Alright, so whenever you have a gear train like this, oftentimes you have a driver and a follower. So I'm going to designate the small gear in this case as the driver. This guy, the big one, could be the follower. And to make an analogy, it's like the case where we had a box pushing into another box. If you remember these problems from the past, you know that it could be the case that somebody from the outside may be applying a force on the one block, which in turn applies a force on the second block. So I could call this block A, and this here is block B. I'll do the same thing with the gears. This could be gear A, and this could be gear B. Now the person who's on the outside applying the force, they push on A. A is pushed into B, so B pushes back on A. Maybe not as hard, perhaps. And then what we see is that A will push on B according to Newton's third law. So now, in order to make the analogy appropriate, there is acceleration, let's say, in this situation of, let's say, 1 meter per second squared. If that's the case, then the person pushing on A, they do have to push harder than B pushes on A. Because the person has to win here in order to achieve that acceleration. If the forces were equal, they wouldn't accelerate, of course. They'd be going at constant velocity. So to make an analogy for the gear situation, it would be like the axle of this gear is attached to something that's making it rotate. That could be like a wind turbine or some kind of wheel in a waterfall. Or it could be just some person twisting the thing with a wrench or whatever. It could be that maybe they're applying the force, like not even at the location of the axle. It could be that they're just pushing the gear manually from the outside. But that's what makes this guy on the left the driver, is because it's his job to accelerate the follower. In the same way that the person's pushing on A, and A is responsible for accelerating B. So to make the analogy complete, this box would be like the follower. The middle box would be like the driver. Alright, so with that in mind, in this particular case, my system is accelerating. This is not constant angular velocity because we have this angular acceleration. Now, as we showed before, angular acceleration could be positive or negative. It's positive if you're making a thing rotate counterclockwise, and negative if you're making it rotate clockwise. This is a positive one relative to the z-axis. So z-axis comes out of the page. So this is going to be my positive x. This is my positive y. Positive z comes out. So that's the way he's going to accelerate. So if that's the alpha for him, the teeth have to lock together. The teeth are where the forces get applied, like from one gear to the other. If this is correct, which way is A angularly accelerating then? Clockwise or counterclockwise? So as this tooth moves through, the tooth that he's going to be in contact with has to move through with him. So that tells us that A must be accelerating clockwise. Alright, so I'm going to call this the alpha for B, and we could also have an alpha for A. I'm going to leave that as unknown. I can't assume that the accelerations are going to be equal in value. We have to do a little bit of math to figure that out. Alright, so what can I figure out? One thing that I can assume for sure is that there is going to be only one torque on gear B. Let's assume that A is the one driving him and it's the only thing driving him. So what's going to happen is this tooth here is going to contact a tooth of B. And he's going to apply a force from one tooth onto the other. Well, he's going to be pushed down. Okay, he's going to feel a force from A pushing that tooth downwards. So let's draw a force vector for that. And we just have to think about the laws that we've worked with so far. One thing that has to be obeyed is Newton's third law. It still has to hold here. That means if we have a force of A on B, there must be an equal and opposite force of B on A. If A pushes on B in the downward direction, then by Newton's third law, B must push on A in the upward direction. That's just FA on B is the opposite of F of B on A. Now, knowing this gear's mass and his radius and the force acting on him, we can find out a bunch of stuff about that gear. Alright, so first I would start with a moment of inertia calculation. Let's find the moment of inertia of B. Now, discs have a formula for moment of inertia of 1/2 mr squared. So I'm going to use the mass of B and the radius of B to find his moment of inertia. So his mass 64, radius of 4 meters. It's 512 meters squared. So Newton's second law says this, that the net torque on a system will equal the moment of inertia of that system times the alpha of that system. So I can find now the net torque acting on that gear. It's obviously 512, and the units will be Newton meters. And it's positive because it's a torque that makes the thing want to rotate counterclockwise. Now that I know that, I could find the force on the teeth of that gear. The reason I can is because I would now use the other torque formula. This one's Newton's second law, but we also have another formula, and that's just the definition of torque being a cross product of R and F. So we know what the torque needs to be, 512 Newton meters. We actually know the radius of the gear is 4 meters. I could find the force of A on B. Okay, so let's divide and find that force of A on B is 128 newtons. Okay, now what does that imply to me? It implies that if this is 128 newtons, then gear B must be also applying 128 newtons back on A. And the thing is, though, even though B pushes up on the tooth of A doesn't go that way. A doesn't rotate counterclockwise. He's got to stay in contact with B. He's got to push through. That's why he's the driver. Okay, so that means that that's not the only force that's acting on gear A. There's also this guy. The person is applying a force upward on that other tooth, which could equally make the thing want to angularly accelerate. So let's now draw a little vector here showing that this guy is pushing up on that tooth. We need to figure out how much force is that person pushing with. I'll call it force external. Now that's going to take a little bit of work to find out what the external force is here. First thing we got to find out is we got to know the angular acceleration of A. We don't know that yet. Can't assume that they're the same. Alright, so what do we know for sure though about those teeth? One thing for sure is that the speed that they're moving with has to be equal. So we would call that just V, like the V of A has to equal the V of B. That's a linear speed though. So what about angular speed? So there's a formula for finding angular speed from linear speed. Formula is V equals R omega. So what this is a formula that relates like a tangential speed to an angular speed. Let's also look at another one. A equals R alpha. This one relates tangential acceleration to angular acceleration. Now you gotta figure out which gear you want to do it on. I'm gonna start with gear B because I know his angular acceleration. So for B, we would have this. AT equals 4 meters times his alpha. Okay, so your AT then is 4 meters per second squared. That's the tangential acceleration of the teeth. Now that I know the tangential acceleration of gear B, I'll write that here. It's 4 meters per second squared. In order for the teeth to interlock, it must be that the tangential acceleration of gear A is the same. Otherwise, they wouldn't mesh together like a zipper. So with that in mind, I could use this formula to solve for the alpha of A. Plug in the 4. Put in the radius of gear A. And then solve. To reveal that the angular acceleration of A is twice as large as the angular acceleration of B. So that's what goes here. -2. Next, we want to find the size of the external force that the person's applying on gear A. First, I'll use the idea of the net torque being the external torque plus the torque of B on A. There's a force of 128 newtons with a lever arm of 2 meters pushing counterclockwise on the gear. So that's going to be the torque of B on A. For the net torque, I'm going to use I alpha. I is the moment of inertia of A, and then here I'll use the alpha of A, which I determined earlier to be -2. For the moment of inertia of A, I'll use 1/2 times the mass of A times the radius of A squared. Plug in the -2 for alpha. It's a 16 kilogram disc. .2-meter radius. Looks like -64. Okay, so now we'll subtract. External torque must be -320. Now that we know the torque that the person's applying, we can use the lever arm of 2 meters, the radius of the gear, to find out the force that the person must be applying. I'll put in the 2 meters and then divide to reveal. It's 160 Newton force that the person is pushing up with.